So it would seem that the audio had cut out of lecture 15, and I would like to continue from the point at which the sound cut out and finish off that lecture for you. So rather than reiterate everything that was being said in lecture 15, I'll just summarize by saying we were discussing the application of conservation of momentum, and we were applying that to a couple different examples. This example here has to do with bumper cars and the collision that takes place between a father and his son. In the problem statement, it tells us that the dad is traveling in the same direction as the son, and that the son's final velocity is also in that same direction as the initial velocity. And so what we would like to know then is what the dad's final velocity is. So conservation of momentum tells us that the change of the momentum of the system in the absence of net external forces should be zero. We can treat this as a one-dimensional problem since they're basically constrained to a horizontal plane and everything is going in the same direction. So what this means then is that the initial total momentum in the x direction has to equal the final total momentum in the x direction. What does that momentum consist of? In the initial state, you've got the mass of the dad times the dad's initial velocity, plus you've got the mass of the child times the child's initial velocity. And then in the final state, you have essentially the same two terms, only now we're talking about their final velocities. We need to solve for the dad's final velocity. So collecting all of our terms and isolating the velocity of the dad, I'll let you work through the algebraic steps on your own, but the final statement should look something like this. Okay, and when you plug in the numbers that are given in the problem statement and compute this, what you should find is a final velocity of 1.2 meters per second. So always when we problem solve, we should check our answers for sensibility, and the dad is much more massive than the son is. By the way, this problem includes the mass of the car and the dad, so it's easy to just plug in those numbers that are given. But the dad is much more massive, and so his velocity is not going to be as great after this collision compared to his son's velocity, who is less massive. And so that all checks out and is sensible. Okay, moving on to another example. That example with the bumper cars was an example of what we would call some sort of an elastic collision. Maybe not perfectly elastic, but one in which you are essentially looking at a situation where two objects are bouncing off of one another. The other end of the spectrum is the inelastic collision, in which things mostly stick together. So this example looks at that type of collision where you have two planetesimals that are colliding and sticking together in the early solar system to create a larger planetesimal as the process of planet formation unfolds. We're going to treat this, though, in a very similar way to what we did with the bumper cars. Whether you're talking about elastic collisions or inelastic collisions, in the absence of net forces, momentum will be conserved for your system, so you can essentially set it up the same exact way. In the problem statement that you read here, you can see that there's also this also nicely reduces into a one-dimensional problem because you have a planetesimal traveling at a certain velocity and another one in direct opposition, meaning that as one is traveling, say, in the negative x direction, the other is traveling in the positive x direction, or y direction, however you would like to define your coordinate system. And then in the final state, once they've stuck together, they're traveling in the same direction that the first planetesimal was traveling in originally. So again, this is just really a one-dimensional problem. We're not looking at any sort of two-dimensional situation here. All right, so we're going to start off the same and say that the total momentum of the system will remain unchanged from initial to final state. And so the initial momentum of the system has to equal the final momentum of the system. What does that mean? Well, we've got, we could call the first one M1, and the second planetesimal would be M2. Okay, this is what we're actually looking for, is the mass of the second one. Okay, so M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. So we set it up essentially the same way as the bumper car example. Okay. The other thing to note is that they have the same velocity in the end. In other words, V1 final equals V2 final. So this right-hand side of the equation can simplify, and we can write it as the sum of the two velocities times some final velocity, which is the same. Okay? Now, it's the mass of the second planetesimal that I need. So I need to gather two like terms, right? I've got the mass in this term and the mass in this term for the second planetesimal. I've got to combine those together and isolate that second mass. So when I do that, I would have, as my first step, getting all of the mass 1 on one side of the equation and all of the mass 2 on the other side of the equation. That's how I would start with it. So I would have something like this. Right? And then I could factor this mass 2 out and then divide both sides by what would be in parentheses. So this will give me an expression which looks like this. And that will equal my mass 2. Now, at this point, we need to mind our signs and pay attention to the fact that the initial velocities were going in the opposite direction from one another. So if I am to, say, define the direction of V1 as being my positive x direction, then I need to make sure when I plug in V2 initial that I have, I'm plugging in for this term a negative 1.0 meters per second right here. Okay, so I'll have a minus and then another minus sign, so this bottom, this denominator ends up being the magnitude of V final plus the magnitude of V2 initial, because I've got a negative and then another negative in here. Okay, so when I plug in those numbers, in other words, I should have mass 1 times, in the numerator, 3.5 meters per second, and in the denominator, I will have 2.5 meters per second. So multiplying that by mass 1 will give me 1.4 kilograms for a final answer for mass 2. Okay, notice that we didn't worry about any minus signs until it came time to plug in the numbers. You may see in your book or in other examples elsewhere that they may have gone about this problem a little bit differently, and instead of waiting until this step to plug in the minus sign, they would have said, well, right here, I knew that these were going in the opposite direction, so I'm going to put a minus sign in here. I would caution you to maybe rethink the wisdom of doing that and plugging in the minus sign preemptively, just because you don't want to get turned around with your signs and wonder if you need to plug in another minus sign. It's similar to the issue of plugging in that minus g whenever we use our kinematics equation and then being tempted to plug in another minus sign for the 9.8. There's no need to do that. We don't need to take account of the signs until it's time to. So I would urge you to just kind of leave everything positive, leave it set up as you see here, and then when it comes time to plug in the numbers, think about whether or not there needs to be a minus sign involved. Okay? So that's the example of an inelastic collision in 1D. So we've done elastic collision in 1D and inelastic collision in 1D. I want to do an example of a two-dimensional type of conservation of momentum problem, which is somewhat like an explosion. So the hardest part for students to grasp with this example is generally the setup. Oftentimes students get hung up on this first part, that this plate is being dropped vertically. And so they worry about what happens to the vertical part of this problem. Well, that's just to set it up. What the problem is trying to get at is that it's giving you a mechanism by which these shattered pieces of the plate are all going to scatter at different velocities within the plane of the floor. So I'm no longer concerned with the z direction that would be going, up out of the screen or into the screen. That these pieces are said to have no component in that direction, right? So all I'm looking at in the end is really, okay, the thing exploded effectively in the XY plane. And all of these pieces of the explosion that go off in the X and or Y direction have to conserve momentum such that the initial momentum in the XY plane was zero, right? As it was falling completely vertically, it had no momentum in the X or Y direction, and then when it hit the floor, the different pieces went off in different directions in the XY plane. So that all has to add up to zero, right? So the change in momentum of your system is still zero in this two-dimensional problem, but what it means is that I'm starting off with an initial momentum equal to zero. Okay, so when I add up all of these pieces of the plate, I need it to add up to zero. Okay, so that's the setup. Pause the video and think about it. Listen again if it doesn't still make sense to you. We can discuss it, but that's the setup. And so moving forward with it, let me go to the next screen where I have a little bit of more room to write. We have to consider both the X and the Y direction. Now, a lot of information is given to you on the figure that you see here. However, you have to be careful with these kind of figures, because whenever we are resolving vectors into components, if this is my X direction and this is my Y direction, as we traditionally do, whenever we're thinking about taking the component of, for example, V2, it's really straightforward. I know that there will be a component in the X direction, which will be related to V2 times cosine of 45 degrees, and in the Y direction, V2 times sine of 90 degrees. But what about V1? What's happening there? Notice that they're defining an angle with respect to the y-axis. If I'm going to resolve that vector into components, I need to tread carefully and make sure that I plug in the right sine or cosine or the right angle that I need. The way it's pointing there, for example, if I use 25 degrees, am I going to get any negative component in the x direction? No, right? My calculator will return a positive value because this is just a reference angle. This isn't the actual angle that I generally use as measured with respect to the positive x-axis. So to make my life easier, I mean, I could do one of two things. I could say, okay, well, I'm just going to use the angle that they've given me and figure out whether I need to use sine or cosine or a negative in there in order to get the right components based on what I see. Or the other thing that you can do is just make sure that you define the angle with respect to the x-axis, the positive x-axis. And instead of this 25 degrees being the angle that you would use for your theta, I'll use this whole angle instead, which is, well, what is it? It is 90 degrees plus the 25 degrees. So here, this is 115 degrees, right? And I'll call this my theta 1. This will be theta 2. What is theta 3? Well, theta 3 is all the way around to here. Theta 3 is 270. Okay? All right, so once we've figured out the angles, then we can look at what's happening in the x and y direction separately, just like we've done with Newton's laws problems. So in the x direction, let's take that first. The initial x momentum has to equal the final x momentum. It's 0 in both cases, x and y, initially. So what this is saying is that 0 in the initial state has to equal the momentum added up from all of these pieces, whichever ones have x components to them. Now, M3, you can see, does not have an x component at all, so I can just omit that from my sum. But I do have M1 V1 in the final state, and I've got M2 V2 in the final state. Okay? But I need to make sure I'm only taking the x components of these, right? And so to be more explicit about that, that means that I want M1 V1 times cosine of theta 1, where, remember, theta 1 now we're careful to say is 115 degrees, plus M2 V2 times cosine of theta 2, where theta 2 is 45 degrees. Okay, so this gives me an expression that I might be able to use, but the problem is that I don't know mass 1 or mass 2. In fact, that is what I'm looking for, mass 1 and mass 2. So this equation has two unknowns to it. And anytime we have an equation with two unknowns, that tells us we need a second equation, right? Two equations for two unknowns is what's required here. But that's okay because we haven't looked yet at the y direction. So let's see what's happening there. We've got the y momentum in the initial state that has to equal the y momentum in the final state. So this is telling me that 0 in the initial state has to equal all the momentum added up of all the vectors that have y components. Well, I don't get off easy this time. All three masses have some y component to them. So I've got M1 V1y plus M2 V2y plus M3 V3y. Okay? And so fleshing that out some more, just as we did before, this means M1 V1 sine of theta 1 plus M2 V2 sine of theta 2 plus M3 V3 sine theta 3. Okay, you may already realize that when I plug in that 270 degrees for theta 3, it's just going to result in a negative sign, but that's okay. In the same theme as going off the same theme as what we had in the previous example, we don't want to have to worry about these minus signs until it's time to do so, and it will all work out as long as you plug in the correct values for your angles. So what I can do at this point is I can take this first equation and I can make a substitution into the second equation. So for example, with the first equation that I have in the green dotted box, I could solve, for example, for mass 1. Okay, so mass 1 is then going to be equal to minus M2 V2 cos theta 2 all divided by v1 cos theta 1. Okay, and I can take this and I can plug it in for mass 1 right here. When I do that, and I take a look at the second expression here, I will see that I've eliminated one of my two unknowns, because everything here is going to be in terms of mass 2, and that will be the only unknown on this right-hand side of the equation. Okay, there's a lot of algebra involved here that I'm going to ask you to work through on your own. But if you do that and you isolate the mass 2, little hint for you, you should end up with a sine theta 1 over a cosine theta 1 in this first term, which you can combine into a tangent just to make your life a little bit easier when you're trying to compute it. But then when you crunch through all of the numbers, what you should find once you isolate mass 2 and solve for it is that mass 2 is equal to 0.92 kilograms. Okay, once I know that, I can take this mass 2 and I can plug it into this green expression and solve for mass 1. And when I do that, I will find that mass 1 is equal to 0.97 kilograms. Okay, therefore I will have solved for both of those masses, and I can check and make sure that makes sense. The mass of the third part is 1.3 kilograms, so something around 1 kilograms for each shard of the plate seems sensible. Okay, so one of the things we talked about in connecting conservation of momentum with what we already learned about Newton's laws was that we could think about the F equal ma, Newton's second law, in terms of a change of momentum instead, because we said that really what is change of momentum, it is your mass times your change of velocity, typically, is if the mass is staying the same. And then we see that this change of velocity over time is the same as acceleration, right? And we get back our Newton's second law. But what does all of that mean? If you want to think about what we've been looking at in terms of collisions and explosions, it's a system. It's usually, more than one object involved. And so we're looking at the mass of your system and the acceleration of what exactly? Well, it's really the acceleration of the center of the mass of your system. So this is where this concept of center of mass can start to make sense to you. If you think about, for example, a projectile like we were looking at in Unit 1 that follows this characteristic parabolic trajectory. If this projectile were, say, a firework and then it explodes at this point in its path, all of these different pieces of debris may go off in different directions, but the center of mass continues under the influence of gravity to follow this parabolic shape, just as it would have if it hadn't exploded, because momentum has to be conserved. So it's important to make that understanding of where the center of mass is in the scheme of things, in the scheme of interactions and collisions. And so how do we actually compute the center of mass? This is your formula that appears in your book, and we're going to talk about how we can generalize this formula. So if you have a system of objects and you want to locate the center of mass of them, here's an example, a simple example where you just have two objects. Now, what would we do if we had three objects? You might be able to generalize from there that the location of the center of mass is just going to be, we're just going to sum up all of these masses that are involved, right? And there are vectors from some origin, all divided by the sum of the mass of the whole system, right? And since this is a vector sum here, what that means is that we've actually got to think about where the X center of mass is and where the Y center of mass is and Z center of mass. So, you'd have to find in each direction where these locations are. So you can kind of think about it as a weighted sum. Notice that in this simple example, the center of mass isn't directly in the center between mass 1 and mass 2. So this might have something to do with mass 1 being further away and or more massive, and you've got to think about where that center of mass is. The more massive mass 1 is going to be, the closer the center of mass will be to that mass 1. So an extreme example of that might be our solar system, where the center of mass of the solar system, all the mass of all the other planets in the solar system is small compared to the mass of the sun. So the center of mass of the entire solar system is actually located within the sun itself. Okay, so that would be like moving the center of mass all the way to this mass 1 here. Okay, we're going to talk more about center of mass in lecture 16, and you'll get to see that. But you might be able to anticipate that you could think about these little individual masses as part of a bigger collective macroscopic object, in which this is like a little piece of mass and a little piece of mass, and then you can think about how this sum might turn into an integral for some extended body. More on that in lecture 16.